It's a pleasure to be here. I think my first time at the University of Oregon, but it's always great to be back on the West Coast. So I want to talk about undecidability in number theory. And so this is, the first talk is going to be more of an overview talk. So let me tell you some problems connected with undecidability. So I want to talk about Hilbert's 10th problem. I'll always abbreviate it as H10. And so the original problem posed by Hilbert was phrased over the integers. So this, I'll talk about the 10th of his famous 23 problems that he posed in 1900. And so the 10th asked to find an algorithm that decides given a multivariate polynomial equation f of x1 through xn equals 0 with coefficients in z. Whether it has a solution with the xi's integers. And so this was posed in 1900. It remained open until 1970. When Matiyasevich showed that no such algorithm exists. And so this was based on work by Martin Davis, Hilary Putnam, and Julia Robinson. And so usually for short, we just say that Hilbert's 10th problem is undecidable. So there's no algorithm that decides whether polynomials over the integers have integer solutions. And so I want to talk a little bit about, say a little bit about how this proof works. So in this proof, these 4 people showed that over the integers, 2 types of sets are the same, namely Diophantine sets and recursively enumerable sets are the same. And so I'm going to say a little bit about what that is and define them. And before I do that, let me just point out that even though the original problem is stated with just one polynomial equation, you could also consider systems of equations because because say you have 2 polynomial equations and you want to look for a simultaneous 0 of them, well, that's the same thing as asking that the sum of the squares have a 0. So that means you can also transform systems of equations into one. So you can also think about the problem as asking about systems of equations. So I'd mentioned that the proof, the undecidability proof worked by showing that 2 types of sets are the same. So let me make this definition here. So I'm going to say that a subset q of some power of the integers is Diophantine, say over z, if there is a polynomial f, so it has some variables x1 through xk, in which we'll plug in vectors from c to the k, and then some other variables y1 through ym should have integer coefficients. And such that Q is exactly the set of k tuples, so that when I plug it in, there is a solution in y1 through ym. So f of x, y1 through ym is equal to 0. And so let me just give one example of such a Diophantine set. So we'll do 2. So the standard example that's always being used is that the natural numbers are Diophantine over the integers. And so that means we want to find some polynomial equation that describes what it means to be a natural number. And then we just remember Lagrange's 4-square theorem. So every natural number can be written as a sum of 4 squares. And of course, anything that is a sum of 4 squares must be a non-negative number. So we can just say that x is a natural number. So n is our q here, if and only if there exists y1 through y4, y1 squared plus y4 squared minus x is equal to 0. So that is the Diophantine definition of the natural numbers. And so this would be our polynomial in the variables x and y1 through y4. So that's the f polynomial here. And much more difficult, and sort of leading up to what I want to talk about next, is that the set of primes is also Diophantine over z. Now, I'm not expecting anybody to just shout out the defining polynomial for the primes. It sort of fits on one page. People have been working on reducing the number of variables, but so this is not something that you can just like write down in one line. But so why should something like this even be true? Well, because there's another notion, being recursively enumerable, that over the integers coincides with the notion of being Diophantine. So let me make a second definition here. So a set Q is recursively enumerable or RE, or sometimes people use computable, but since so that's more preferred by logicians or recursion theorists. And well, so what does it mean? It just means if there is an algorithm and by algorithm I just mean you can think about it as a C program with just like where there are no memory constraint, a finite C program. You can think about it as a Turing machine, if you've heard of those before. All of those are equivalent, and so we want to have an algorithm that prints Q, possibly with repetitions, we don't care about that, when left running forever. And so, for example, the primes would be a recursively enumerable set, because certainly anyone can write a program that just loops through the integers and only prints the prime values. And then so this is recursively enumerable, or short RE. And then there's also a stronger notion, and that is the one of being recursive. And that is if there is an algorithm that decides membership. So that means you wrote some kind of computer program, and I enter an element, an integer into it. Some integer a, and now it answers yes if a is in the set, but it also answers no if a is not in the set. So that means for recursive sets, you can list the elements that are in it, but you can also list the elements that are not in it. So that means so every recursive set is recursively enumerable. The backwards implication is false, but it is true that a set is recursive exactly when both the set and its complement are recursively enumerable. And so it is a fact, and you can, maybe you've seen this if you've taken some computer science class or some logic class from the halting problem. You can construct sets that are recursively enumerable but not recursive. So there are sets that are RE but not recursive. And so the big theorem, usually the first three authors are listed in order, Davis, Putnam, Robinson, and then Matiyasevich gets put at the end because he's the one who finished it off. So other people do different permutations, but so this is a very common one. So this is what is sometimes referred to as the DPRM theorem. And so it is a very powerful theorem that describes Diophantine subsets over the integers. Namely, it says that a set Q that is a subset of the integers is recursively enumerable if and only if Q is Diophantine. And so in particular, this shows that the set of primes will definitely be Diophantine because it's clearly recursively enumerable, and has some other implications too. So let me just say, so the hard direction is to show that every recursively enumerable set is Diophantine. The backwards direction is much easier. So let me just say, so one direction is easy. So Q Diophantine implies certainly that Q is recursively enumerable. What would you just do? Well, you would just, if your polynomial looks something like f of x, y1 through ym, then you would just loop over all possible tuples in z to the m plus 1. You plug them into this polynomial, and you print the first coordinate whenever you get a 0. That will eventually list all your elements in the set Q. And so that shows that Diophantine sets will certainly be RE, and the backwards direction is the hard direction, and I can't really say anything meaningful in a short period of time about that, but so that was the backwards direction is the heart of the proof of the DPRM theorem. What I want to focus on now is showing how the DPRM theorem implies the undecidability. Yes?
So the reason that it doesn't imply recursiveness is that we have to produce yes or no in finite time.
Right, exactly. So you know if you let your algorithm run and it hasn't produced a yes net yet, you don't know, will it maybe produce a yes in 5 million steps? Or will it, if you leave it running forever, will it just never find the yes? Yeah, so that's exactly the problem. And that would be avoided if you could also enumerate the complement. Yeah. So, and here, so this fact that a set might be RE but not recursive is exactly how how they were proving the undecidability of Hilbert's 10th problem. So let's say Q is recursively enumerable but not recursive. And so then the DPRM theorem implies that Q is Diophantine. Let's give the defining polynomial a name. So let's say it's f a y1 through ym. And now, if there were an algorithm for Hilbert's 10th problem, then for each a in Z, we could ask whether there exists y1 through ym such that f of a y1 through ym equals 0. Well, and if they exist, then A must be in Q, and if they don't exist, then it's not in Q. So that means the algorithm for Hilbert's 10th problem would let us decide membership in Q. And that is a contradiction. So membership in the set Q, and this is a contradiction to the choice of Q, because we chose one that is not recursive, so we should not be able to decide membership in it. Yes, so that means, so Hilbert's 10th problem would allow us to decide membership. And so this powerful theorem completely describes the Diophantine sets over the integers, and in particular implies that Hilbert's 10th problem over the integers is unsolvable. Okay, so now, and in fact, people were stuck on Hilbert's 10th problem, the original version, for a while. And whenever mathematicians are stuck on a problem, they change the problem. So already before the original problem was resolved, they said, well, we don't just have to restrict ourselves to the integers here. We can ask the same problem with over some other commutative ring R, and we get Hilbert's 10th problem over R. And so that now we're just going to say we're going to look at equations with coefficients in R rather than integer coefficients. And now we also want solutions in R. Yeah?
So are the recursive sets the same as the Diophantine sets where you can eliminate the existential quantifier? Or, I mean, so if you get rid of their exist, then it's recursive, but is the other?
I'm not sure. I don't think so. Yeah.
So over here, you really mean all R as coefficients, not just like.
So for the purposes of my talk, so in general, I want to only have coefficients in something that I can sort of input into a Turing machine. So I want something that's, say, finitely generated over Z or something like that. So, but everything I'm talking about today will be subrings of Q or number fields where this is going to be possible. But you're absolutely right. If this was some function field over some uncountable field, I would want to restrict to some subset like Z adjoined x1 through xn or something like that. Yeah, but so for the purposes of today, we can just look at this definition. And so this, asking for a solution, that I can always ask over the full ring no matter what it is, since that's just a yes-no question. Yeah, yes? Did you have a question? Okay, so that means, and now the biggest open question here, which was already considered by Hilbert, and some say he fully expected that there would be an algorithm for the integers, which would have also given an algorithm for the rationals. So what if you look at rational equations and you want to look for rational solutions? Now this is also, you can of course also interpret this geometrically, because if you have a system of equation that's going over, say, over the rationals, that's going to cut out some variety over Q, and basically you're asking if this variety has a Q rational point. Now, when you think about it like that, it's an extremely hard problem. So already for genus 1 curves, if there aren't some obvious points, like we can't even decide if a genus 1 curve over Q or over a number field is going to have a point. And so certainly, so since that's just going to be a subcase here, so I think most people seem to think that this should be undecidable. And so I want to talk a little bit about how you would want to try and prove something like that. So the notion that is the key definition here is already on the board. And so we can certainly extend the definition of being Diophantine also to now commutative rings R. So now we're going to take subsets of R to the K. We call them Diophantine over R if and only if there is a polynomial with coefficients now in R, so that Q is exactly the set of K tuples in R for which we have y1 through ym in R, such that f of x, y1 through ym is 0. So I'm just replacing Z with R everywhere. Yeah, and so that's going to be one of the key definitions. And I'll show in a little bit why that's related to actually proving whether or not the problem for a ring is undecidable or not. So, but let me mention now some. So the problem is known to be undecidable for Z. It's open for R equals Q in number fields in general. And so let me mention some results where it's known to be decidable and some where it's undecidable. So here are some decidability results. So obviously, the problem is decidable for finite fields because you can just loop through all possible tuples, plug them in, and see if there is a solution. It's also, because of Hensel's lemma, possible to do it for p-adic fields and also for real closed and, of course, algebraically closed fields. And so the real closed fields is a technique called elimination of quantifiers and was done by Tarski. Now, it's also known to be undecidable for a bunch of rings. So it's undecidable for some rings of non-integers in number fields, finite extensions of Q. And so this was work of a bunch of different people, Denef, Lipschitz, Feidas, Schlappentock, and Poonen. And you can also show, and that was done very recently by Maser and Rubin, that it's undecidable for arbitrary rings of integers, so no restrictions. So these usually need elliptic curves with some properties. And it's undecidable for arbitrary rings of integers if the Shafarevich-Tate conjecture holds. And so this is a result by Maser and Rubin. Yep, and so it's like it's a, you can sort of, you don't need the full Shafarevich-Tate conjecture, you need it for certain cyclic extensions. Yeah. And so then you have a bunch of other fields. So, well, if you're sort of looking for the analog of number fields or Q over finite field or in characteristic P, you have function fields of curves over finite fields. And this is work of Schlappentock, Fidas, Videla, and myself. You also have p-adic function fields, so function fields over the p-adics. That's work of Kim and Rausch and myself. And you have function fields in at least two variables over C. And that's work of Kim and Rausch, Moret-Bailly, and myself. And so what I want to talk about today a little bit is how close we can actually get to Q. So we can get certain large subrings of Q for which the problem is still undecidable. So this was done by Poonen, and then a generalization of myself and Graham Everest. And the same construction can also be done for a number field. And so the original case was done by Poonen and Schlappentock. And then there was a generalization by myself, Schlappentock, and Graham Everest. And so I've defined the notion of a Diophantine set, but I haven't really said how it's related to proving undecidability. And so the relation to undecidability is the following. So we have the following theorem. So what we would like to do is somehow use the original undecidability result over the integers and transfer that and get from that also undecidability over other rings. And so the following theorem, so let's say R is a domain of characteristic 0, whose quotient field is not algebraically closed. I, in fact, can actually drop that, but so let me not write it down. And so then the following theorem holds, namely if Z, and so this has been used by many authors working on undecidability, namely if Z is Diophantine over R, then Hilbert's 10th problem for R is undecidable. And so that means if we can somehow find a polynomial f inside some ring R that exactly cuts out the integers, then we immediately get undecidability for the bigger ring R as well. And so that is how this was proved for some of the ring of integers. And so that was sort of how the first approaches went. And so let me just say a sketch of the proof. So the proof is by reduction. So we're going to assume by contradiction that H10 over R is decidable. And we will show that this gives an algorithm for Hilbert's 10th problem over Z, which we know does not exist. So how does this work? So we'll just assume we have an algorithm for Hilbert's 10th problem over R, and now we want to cook one up for Hilbert's 10th problem over Z. So we want to cook one up for this problem. So that means we're going to give ourselves some polynomial equation with integer coefficients, and we want to somehow use the algorithm for R and the Diophantine definition. Well, as a first step, we can just ask, well, does this have a solution over R? And the algorithm for Hilbert's 10th problem over R is going to tell us yes or no. But we can also say, only give us solutions x1 through xn in which the xi's satisfy this polynomial equation that forces them to be integers. So that means we can say, give us a solution and give us one in which the elements in the solution are forced to be integers. And so that gives us an algorithm for Hilbert's 10th problem over Z. Yep. So let me just say it in words here, since I don't have time to write down the details. And so this kind of reduction argument is very powerful and can be used in a lot of cases. But sort of once you get to more, so and for example, if you're just sort of looking at sort of the smallest extension of the integers, like say Z adjoint I, yeah, there you can, like using Pell's equation, come up with a definition, with a Diophantine definition of Z, and you can sort of do it in like small extensions where you can control, say, the units. But once you get to bigger extensions, you really need more flexibility, and really actually cutting out the integers exactly seems very hard. So what people have come up with is the notion of a Diophantine model, which is just an infinite set on which you can define with equations addition and multiplication. And so that gives you more flexibility, and you can still prove that if there is such a Diophantine model of the integer, then it's still undecidable. And so once you have that in play, then you can use more complicated sets for your Diophantine model, for example, rational points on an elliptic curve on which you already have addition, and then you need to define multiplication. So that's the motivation. So let me just define here what this more general object is.
Can I interrupt again?
Sure.
Just to check the logic of the sketch of the proof of the theorem.
Yes.
So since the p-adics have a decidability, we don't know if Q is Diophantine inside of the p-adics? Or is there really something with Z in this theorem?
No, you could, so if you can replace Z by any ring over which Hilbert's 10th problem is undecidable. So there are some other rings also where it was more useful, like I used some argument where I defined some quadratic extension of Z inside the ring or something. Yeah, so you can replace Z by anything for which you know the problem is undecidable. Yeah.
But also, since it's a contradiction,
Mm-hmm.
if I could find Q in a Diophantine fashion over the p-adics, and since I have positive decidability for the p-adics, wouldn't that answer the open question for Q? I'm just checking.
Oh, okay. So if you have Q, so I'm not sure if that.
That's fair. I'm interrupting you.
Yeah. Yeah, but I'll talk to you about it afterwards.
Sure. Sorry.
That's okay. So let me just define this more general notion. So here is a Diophantine model. Of the integers, and we need both addition and multiplication in a ring R, is a Diophantine set. That sits in some Cartesian product of R, and that comes equipped with a bijection phi from the integers to the set S. So it's just as a set in bijection to the integers. So there's some map that sends an integer n to some element xn in the set. And then we just want to have that the addition law that we have on Z and the multiplication law, those get transferred under phi to addition and multiplication on the set S, some induced law. And we want that those are Diophantine. So that's such that under phi, the graphs of addition and multiplication are Diophantine subsets of S cubed. And so that means, so what does the graph of addition looks like? It just means xn, xm, xl, for which n plus m equals l. So that should be Diophantine. And xn, xm, xl, for which n times m equals l. That's the graph of multiplication. These must be Diophantine over R. And then the same argument as before the same proof shows that if R admits a Diophantine model, then Hilbert's 10th problem is undecidable over R. And so now this was the approach taken in many of these arguments in many of the results that I listed, in particular in these results that I mentioned as large subrings of Q and large subrings of number fields. In particular, it's also possible to construct a Diophantine model of the integers if your ring has positive characteristic. So of course you don't have the integers as a subring, so obviously they can't be Diophantine, but it's still possible to construct a Diophantine model. And so here is also where elliptic curves come into play, because so one way that people have been looking at these things is, so if they want to prove undecidability either over some ring of integers or say some function field. So in the function field, one approach has been, well, take an elliptic curve that has rank 1, then, and I don't know, take some large multiple of your generator so that or just assume that there's no torsion. Then that generator of infinite order will give you certainly a set S that's in bijection to Z. It's also going to be Diophantine because it's just going to be all pairs x, y satisfying the elliptic curve equation. You also get kind of for free that the graph of addition is going to be Diophantine because the addition law on an elliptic curve is just given by equations. And then the only thing you have to worry about, and that's usually a very big worry, is what you're going to do with multiplication. And so for function fields, when you can define valuation rings in a Diophantine way, those have been amenable to this approach. And the approach has also been used here for large subrings of Q. So let me just say a few more words about that in my last 15 minutes. So we have some elliptic curve equation. So let me just do like a simplified Weierstrass equation here with, well, everything we're going to be doing will be over subrings of Q over number fields. Let's just pick our A and B and Z. So this is going to cut out is going to define an elliptic curve over Q as long as the right-hand side does not have any repeated roots. The points x, y satisfying the curve equation together with the point at infinity form an abelian group. And the group law is given by equations, meaning if I give you x1, y1, and I want to add it to x2, y2, there's just an explicit equation what the formula is for x1, y1 plus x2, y2 in terms of the coordinates x3, y3 that the sum of the 2 points has. So that's the kind of object I want to use here. And so I want to look at, and so why am I doing this? So why am I looking at large subrings now? Well, it seems like at this point, and I'll say more about it in my afternoon talk, so it seems pretty easy. Well, if you want to prove the biggest open problem, just find a Diophantine definition of the integers over Q. Just find some polynomial over Q that cuts out the integers. Well, there's such a thing called Mazur's conjecture, which I'll mention this afternoon. And if Mazur's conjecture holds, then not only is Z not Diophantine over Q, it also doesn't even have a Diophantine model. So that means this sort of proof through reduction might not work for Q if Mazur's or if we believe in Mazur's conjecture. But we could at least ask, well, how far can we push it? Like, how big of a subring can we get of Q and still prove undecidability with this approach of using the model? And so that is what Bjorn Poonen did. So that means we're going to, he was the one who first started looking at this question in this way. And so, so that means, so we have some ring R that contains the integers, is contained in Q. And if we have P, and let that just be the set of primes, then we know what all of these R's look like, because they're just, you just take a subset of the primes and invert them. So that just means you're allowing denominators in some subset of the primes. So every such R is of the form Z adjoint W inverse for some W that sits inside the set of primes. Yeah. And so by W inverse, I just mean the primes that are in W I allow as denominators. So those are A over B, with A integers and B are going to be in the set W. Yeah, and vice versa. So the rings, so every subset of the primes gives rise to a ring, and also every ring gives, is determined by the set of primes. So this is just the one-to-one correspondence that I get between the subsets of the primes and the subrings between Z and Q. So now there are sort of two extremal points here. Well, I could just say, well, how about if W is finite? From Matijasevich's theorem and work of Julia Robinson, it just follows immediately that this is undecidable. So, and at the opposite end of the spectrum is, well, what if W contains all the primes but finitely many? So what if the complement of W is finite? Well, in this case, one can also prove with using work of Julia Robinson that the problem for this ring has the exact same answer as the problem for Q. So if we want to step away right now from sort of the hardest possible thing, and we also don't just want to reprove something that's already known, the kind of sets W that we're looking for are W's that are infinite and whose complement is also going to be infinite. And so what are the sort of biggest possible W's that happen there? Well, they're going to be sets W's in where the natural density is going to be as high as possible. So natural density of a set of primes just means you take your elements in your set up to a certain point, and you divide by the number of all primes up to that point, and then you just let the bound go to infinity. And so the best you can hope for is, of course, natural density 1, and you can certainly have that a set has natural density 1, and yet its complement is still going to be infinite. So that is possible, and so that is what the first theorem of Poonen from 2003 showed. So he showed the following. So there exists a recursive set W of primes of natural density 1 such that Z such that so let me just state the result. H10 for Z adjoint W inverse is undecidable. Is it possible to read the bottom of this still, or? And so what he did in the proof is he constructed a Diophantine model of the integers over Z adjoint W inverse. And it used points on an elliptic curve. But we can already see that because this thing, so I mentioned how the elliptic curve approach would go for fields, for these function fields where it's been very fruitful. But over rings, which these guys are, it's much trickier because if you take a point and you take a bunch of multiples of your point, they of course don't have to stay in the ring. So if you just take a point even just with integer coefficients and you take large multiples of it, eventually you're going to just get rational coefficients. So sort of that means sort of the set W comes last. So first you start with a point. Then you construct certain multiples that you want to take, and then you say, well, W is everything that shows up in the denominators of those multiples that I want to take. But you are in, and so then what this boils down to is that in this model, you're not just taking all the multiples, you're only taking certain prime multiples of your point, and then use theorems about elliptic divisibility sequences that show that you get enough new divisors in the denominators when you take large prime multiples of points. So this is sort of a very subtle construction here. But it uses elliptic curves. It constructs this Diophantine model. And together with Everest and Schlappentock, we were able to generalize this to number fields and to sort of multiple sets of primes at a time. So let me just finish with stating this theorem here. So let me just say that this uses elliptic divisibility sequences, as does our generalization. And so the statement I want to make is, so now I have a number field, and I have to assume that there is an elliptic curve with k rank equal to 1. Over Q, I know, of course, there are plenty of curves like that. And then what we can do, we can partition the prime into subsets of arbitrary densities and get that for each, then we get a bunch of rings in each of which we invert the primes of that set. And we get that Hilbert's 10th problem is undecidable for all of those rings. So that means we're sort of covering the number fields with a bunch of subrings for all of which Hilbert's 10th problem is undecidable. Unfortunately, there's just like no theorem that tells you like that the union of such a thing would also be undecidable. But so let me just state it. So, and every collection delta 1 through delta t of non-negative rational numbers, these will be my densities. And if they're going to be densities, then, and I want to make a partition, then they better add up to 1. So adding up to 1. The set, so the prime numbers are now being replaced by the non-Archimedean valuations. So the set of non-Archimedean valuations of K can be partitioned into T mutually disjoint sets. And so these can be, some of these can be 0. So we mutually disjoint recursive subsets. S1 through ST. And then I get that these sets have the prescribed natural densities and for each associated ring I get undecidability. Such that Hilbert's 10th problem is undecidable for each ring of S integers. And so I just get like some ring OK Si. And so this is my notation. This is the analog of Z joint W inverse. So in this ring, I am allowing non-negative valuations and at the places in Si, and everywhere else it has non-negative valuations. So that means I'm sort of allowing poles at these places and nowhere else in this ring. And I should just say, so maybe there's a question of why this word recursive is there. The word recursive is there. If you don't put that in there, then you can't even decide membership in W, and then automatically Hilbert's 10th problem for this ring is going to be undecidable because you can't even, you can just cook up equations that would let you decide membership in W. So the problem is sort of trivially undecidable if you pick your set non-recursive. So to have any meaningful problem here, all the sets of primes that you always pick should always be recursive. And I think I'll stop here. Thank you very much.
Any more work in this diamond rings that don't resemble integers or rationals, things like that? Like non-commutative rings?
Pardon me?
Non-commutative rings, for instance. Has there been any work? Probably not.
Well, then it's sort of trickier to set up the whole definition.
Yeah.
So I don't know if there's a good, meaningful way to define the problem in that setting. Yeah.
So Hilbert's 10th problem over the p-adic numbers, QP is decidable, as you mentioned. And that's an uncountable field, with an analytic structure. Is the proof more analytic, or is it? And a sort of a related question. There's a sort of intermediate field, which is, I guess, what they call the Henselization or Henselian, which is like not as strong as complete, but it's like just big enough where Hensel's lemma holds, and I think that's maybe still countable. And so I wonder about the Hilbert problem over those more sort of intermediate fields between Q and QP.
Yeah, I'm actually not sure what the answer is about that one. Yeah. I mean, in some of these, there are some cases they are still open in sort of power series rings over completed fields or completed rings, but I'm not sure about this. It's sort of, I have always worked on the undecidability side, and sort of the rule of thumb is that all the decidability results are sort of more closely connected to logic. And so I'm more and so while all the undecidability results have all been heavily on the number theoretic side. So I wouldn't immediately have some idea of how to generalize the p-adic approach there too. Yes?
So if we go back to just the basic Hilbert undecidability theorem, there are certainly polynomials, for example, quadratics in any number of variables where the question would be easy to decide.
Yes.
I'm not sure about cubics there. That one sounds
Right.
like it might be the borderline. Are there any results which carve out a sort of reasonable collection of polynomials where the problem is decidable? Quadratics would just be a really simple way of doing it.
Yeah, I think people are still like sort of working on like number of variables or something like that. And so I think so I think maybe 9 variables is going to be already undecidable. But sort of what people have been looking for and have not been successful yet is sort of finding some geometric condition that would like, so everything is sort of in terms of algebraic condition, like degree of the polynomials, number of variables, but not sort of this family of varieties with some geometric property, it's decidable or it's not decidable. So I think very little has been done sort of on the geometric conditions. So I think the answer to your question is no, that there are no like sort of interesting families beyond sort of the obvious quadratic case where decidability is known. Yeah.
On the question of Hilbert's problem over Q, what do people believe?
I think most people believe that it should be undecidable, especially people coming from geometry with like thinking about rational points on varieties. I mean, papers still get written that like say this variety has one rational point, has a point and I found it or something. So I think people would be surprised if there was somehow an algorithm that just solved this. But I will say a little bit more about that in my afternoon talk.